Hello everyone, let us solve this question. Here we are given that there is a particle moving in a circular path of radius r under the influence of the force F as a function of r is minus k by r square r cap. Now while this particle is moving, it has certain angular momentum which is given by mvr. So it is displaced by a distance delta r such that its angular momentum remains the same. When this particle is displaced slightly by delta r, let's say in the outward direction, the inward, this force exceeds the outward centrifugal force so that this particle begins to come in. Due to its momentum, it crosses the mean position and goes further inside. When it comes inside, within distance r, the outward force becomes more than the inward force so that it again goes outside. This motion happens periodically with certain time period, and in this question we have to find that time period. So the inward force is F as a function of r is minus k by r square r cap. This is in the radial direction, minus r cap, which means radially inwards. So the magnitude of the force is k by r square inward. Now when it is moving in this radius r, it is in equilibrium. So the inward force k by r square is equal to the outward centrifugal force mv square by r. So k equals mv square r, k equals mvr into v. mvr is the angular momentum, L. So k equals LV. Now once this particle gets displaced by delta r, in the question it is given that delta r is much less than r. When this particle comes in this orbit delta r, the net inward force becomes k by r plus delta r square, because total distance from center is now r plus delta r, and the outward centrifugal force is m v square by r plus delta r. Net force is this towards the center, inward minus outward, so this is the net force towards the center. Now mv square is k by r. We see that mv square is k by r from here. So let us substitute mv square equal to k by r. So k by r plus delta r square minus k by r, r plus delta r. This is k by r square 1 plus delta r by r square minus k by r square 1 plus delta r by r equals k by r square 1 plus delta r by r to the power minus 2 minus k by r square 1 plus delta r by r to the power minus 1. So we see where this is going. Since delta r is much less than r, this is 1 plus x to the power n, where x tends to 0 because delta r is much less than r. So we can apply binomial approximation here. So this becomes the net force equals k by r square 1 minus 2 delta r by r minus k by r square 1 minus delta r by r, the binomial approximation. So k by r square minus 2k delta r by r cube minus k by r square plus k delta r by r cube. This gets cancelled and this becomes minus k delta r by r cube. So this is the net force minus k delta r by r cube. F equals MA equals minus k delta r by r cube. So A equals minus K by M R cube delta R. A equals minus omega square R, condition of simple harmonic motion. So omega here is under root K by M R cube. Now we can find time period from here. T equals 2 pi by omega. So 2 pi under root M R cube by K. But in the options, the options are given in terms of L, angular momentum, and not R. So we have to substitute here. Since K equals LV, what can we substitute? Okay, so R is K by mv square. Right, K by R is mv square, so R is K by mv square. So this will become 2 pi under root m by K R cube. So R is K by mv square cube. So K cube over m cube v to the power 6. So 2 pi root K square by m square v to the power 6, that is 2 pi K by m v cube. And now finally v is K by L. Putting this here, time period equals 2 pi K by m v cube. So K cube by L cube. So 2 pi L cube by m K square. This is the answer, which is option A.